Okay, cool. Thank you for reminding me, Justin. Okay, so yeah, collisions. There's the three types. All right, so yes, so to Patrick's point, yes. So when I say momentum is conserved in all three situations, yes, that means the total momentum for the system is the same before and after the collision. Okay? So, in order to explain why, a couple quick terms. So the law of conservation of momentum says, in the absence of external forces, the total momentum of a system will always remain constant. So a couple definitions that I think you guys all know by now. The system is just our collection of objects. All right, it'll be usually the two objects that are colliding. An external force would be a force that is exerted by an object outside of the system. Okay, so gravity would be an external force usually, right? If you're talking about the collision of two carts, gravity is an external force. Okay, friction would be an external force. Air resistance would be an external force. Whatever. All right. Collision is a situation in which two or more objects run into each other. An explosion is a situation where two objects are initially in contact and they push off of each other. Okay? So explosion doesn't necessarily have to involve gunpowder. Okay? You can have two objects that are compressed together by a spring, and then you release them, and we say that they explode apart. Okay? Good? All right. So let's justify the law of conservation of momentum. All right? Probably the easiest way to do it is by using Newton's third law. All right, so suppose I've got two objects, object A and object B, and they collide with each other. Okay? Well, they're going to exert forces on each other, right? So here's the force of A pushing B, and here's the force of B pushing A, right? What's true about those two forces? They're equal and opposite, right? So let's find the impulse. What's another way of saying impulse that's better? Change in momentum. Let's find the change in momentum for each of the two things. So the change in momentum for object A would be, well, we're saying that the only forces are internal forces, right? So I want to find the net force on object A and then multiply it by the time over which that has acted. Follow? Oh, well, that force is just the force of B pushing A, and that happened for some amount of time, right? Okay? If you do the same thing for B, what's going to happen? What should be true about those values? Equal and opposite, right? Look, the forces are equal and opposite. And now I'm going to ask a really stupid question. Is A touching B for more time, or is B touching A for more time? They're the same, right? They have to be in contact for the same amount of time, right? So you've got the same amount of force over the same amount of time. That means you've got the same change in momentum. But notice one of them is going to be negative, right? So in this situation, object A is going to lose momentum. That's going to be equal to the amount of momentum that B gains. Okay? So it's like A gave B some of its momentum, but that momentum is still in the system. So we haven't changed the total amount. Follow? Yes?
So it still works if like one object hits another object, but it's moving the same direction.
Absolutely. Yeah. This says nothing about direction of motion. You know what I mean? Like this, maybe this was moving forward slowly.
Negative change.
Correct. Yeah, negative change. This is all about change. Yeah. Then that would be an external force that would affect things, for sure. So yeah, that would not be a situation in which momentum is conserved.
Oh, so only doing momentum.
Well, so what we're working on right now is learning what the law of conservation of momentum says. And so the law of conservation of momentum says, in the absence of external forces, the total momentum will remain the same. So as soon as you put friction in, your momentum is no longer conserved simply because there's an external force taking away some of that momentum. Follow? Everybody good with that? Okay. Now, I made it a little bit of an oversimplification here. In doing this, I assumed my forces were constant. Okay, what if the forces weren't constant? How do you find impulse, how do you find change in momentum if the force isn't constant? You integrate, right? So that would be this. The change in momentum for object A would be the integral of the net force on object A with respect to time. And the change in momentum for object B would be the integral of the net force on object B with respect to time. But look, aren't these forces still equal? Right? Still by Newton's third law, right? Because if A is pushing B with X amount of force, then B has to be pushing A with that same force. So it still works, even if the forces are not constant, by the exact same argument. Cool? All right. There's also a way to make this argument by using the velocity of the center of mass and Newton's second law for a system of objects, but I don't know that it's quite as insightful, I guess, but it does work. Okay? Basically, when you do conservation of momentum, you're writing a weighted average, mass times velocity, right? It's like a weighted average for the velocity of the center of mass. Okay? All right, questions with this? Okay. All right, so let's do a couple examples. There's 3 examples here. One is elastic, one is inelastic, and one's completely inelastic. All right, we'll figure out which one is which. Okay? So, example number 1. A 1,250 kilogram truck is rolling at 5 meters a second when it collides head-on with a 750 kilogram car rolling at 8 meters a second. Immediately after the collision, the car is going backward at 5 meters a second. Find the final velocity of the truck and determine what kind of collision this is. Okay, so when I say determine what kind, I just mean elastic, inelastic, or completely inelastic. All right, so we did a bunch of these last year, right? I hope. All right, so first of all, let's make sure, is this a conservation of momentum problem? Well, it doesn't say anything about friction or anything. It looks like the only interaction is between the truck and the car, so I think we're good, right? Okay, so I guess I would say make a drawing. So you've got a truck and a car. So here's what we know. Mass of the truck. What's wrong?
I said because that's how cars and trucks look.
It's exactly what they look like. I'm sorry. Here. Is that better?
There we go. Now they have windshields, so you can see this morning. Yeah, like, what?
What's it supposed to be?
What were you going for there?
I was just going to be like, you don't know what a car looks like, because that's obviously beautiful.
You don't know what a real
You know what? I didn't know what to say, because I'm just trying to defend
You're trying to
teach.
You're trying to teach. It's entirely you. You're trying to hurt me, Anthony, by not going across with me, okay?
You're going to throw that in my face again, aren't you?
Yeah, I am.
You really didn't have to do that. I
Right.
thought you were past it.
Can I get an administrator down here? We're going to have a fight.
Yes, we're still recording.
Sorry? Oh! All right, you guys, we got 2 minutes to finish this up. Oh, no.
Oh, we got 3 minutes.
3 minutes, okay. Okay, so, all right, so that should be your setup. Start by writing out your givens. You want to be considering what's happening before the collision, what's happening after the collision. A lot of letters, so keep them straight. Notice, everything dealing with the truck, I put a T on. Everything dealing with the car, I put a C on. Cool? All right, signs, yes?
Yeah, I was about to ask.
Cool. So, which way is the truck going before the collision? It's going towards the car, and the car is going this way. Now, notice you might say, well, the car is driving forward. Is its initial velocity going to be positive? Okay, when you start your problem, you need to choose a sign convention. Pick one direction to be positive and one direction to be negative. Anytime a thing is moving in your designated negative direction, your velocity gots to be negative. Gots to be. All right, it says after the collision, the car is going backward at 7 meters a second. So should I make the velocity negative since it's going backward? For the car, backwards is this way, which is positive. Cool? Any problems? All right, so then your solution is just going to be this. Oh, well, I know my total momentum before the collision has got to equal the total momentum after the collision. No negative. The change is equal and opposite. The total is equal. Cool. Did I do the Desert Island money thing last year, the little lab where we were trapped on the island and maybe I just did it with my regular physics kids. No? Okay. It was probably just regular. So never mind. All right. But so look, you guys. So suppose I got $10 in my wallet and Donald has $30 in his wallet. Okay? If we're the only two people in the world, then we have $40, right? That's never going to change, right? If I give him $5, I lost 5, he gained 5. The changes are equal and opposite. But the total is still 40, right? Follow?
I think we did that.
Did we? Okay. All right. So anyway, so real quick, let's write out our equation. So this means the mass of the car times the velocity of the car initially plus the mass of the truck times the velocity of the truck initially has got to equal the mass of the car times the velocity of the car final plus the mass of the car velocity, mass of the truck, velocity of the truck final. All right? Total momentum before equals total momentum after. We did these a bunch last year. Solve it. We will resume this conversation on Friday. Tomorrow, 10 2's due. I don't know off the top of my head. I have it written down somewhere. Anybody get it? Let's see. 50. I don't know. I'm sorry. Okay. I'll have it for you on Tuesday or on Friday.